For centuries, the trajectory of human progress has followed a relatively straight geometric line. Today, that flat plane is collapsing into a violent upward curving acceleration. When confronted with compounding processes, human cognition systematically defaults to linear heuristics. Cognitive scientists identify this baseline failure as exponential growth underestimation. This graph illustrates the problem. The lower curve is standard exponential growth, where the rate of acceleration is constant. But when researchers at the Santa Fe Institute analyzed historical data, they found that actual technological capability follows this much steeper empirical curve. The widening gap between linear expectations and this reality is super-exponential bias. This is super-exponential growth. The relative growth rate itself is accelerating, which means the time intervals required to double a capability are continuously compressing. To accurately predict whether artificial intelligence will trigger an infinite capability explosion or eventually flatline, macroeconomic assumptions are useless. We have to examine the specific microeconomic mathematics operating inside frontier AI labs. The trajectory relies on one highly specific microeconomic variable, the elasticity of substitution between physical research compute and human cognitive labor. If human researchers and physical servers are gross complements, progress is tightly bound to the physical world. Irreducible hardware limits will throttle any attempt at recursive self-improvement. Standard economic models consistently fail to mathematically define this substitution elasticity. Without that variable, it is impossible to determine if the technological singularity is a software-driven inevitability or a physical impossibility. To find that variable, we must look at the internal mechanics of an AI research firm. Here, algorithmic progress is modeled as a differential equation. The rate of change in algorithmic quality, A dot, is driven by a productivity scaling factor, theta, multiplied by the current quality to the power of phi, representing the difficulty of finding new ideas. The remaining variables calculate effective research effort, function F mapping research compute and cognitive labor to a total output, subjected to a parallelization penalty, lambda. The critical threshold for recursive self-improvement arrives the moment an AI agent can successfully execute the tasks of a human AI researcher. At that exact point, the effective labor equation changes. Total labor is no longer a static human headcount. It becomes an endogenous variable, scaling directly with the agent's algorithmic capability and inference compute. Substituting this autonomous labor capacity back into the primary model creates a highly nonlinear feedback loop. The system begins to feed itself. AI firms navigate this loop through static optimization. They continuously calculate the cost of human wages against the rental rates of physical GPUs, minimizing expenditure while maximizing research effort. By tracking how firms change their compute-to-labor ratio in response to these prices, econometricians can calculate the elasticity of substitution, known as sigma. There are two empirical outcomes. In theory 1, sigma is greater than 1. Compute and labor are gross substitutes. Software bypasses the human bottleneck, and the result is hyperbolic capability growth. In theory 2, sigma is less than 1. Running near-frontier experiments requires massive hardware. Compute and labor are gross complements, locking the system to physical manufacturing. The future trajectory of AI, and whether recursive software acceleration fizzles out against hardware limitations, rests entirely on which of these two mathematical realities holds true. If we assume that compute and labor are indeed substitutes, and sigma is greater than 1, the resulting macro capability curve requires an entirely new calculus to measure. We can observe this theory in practice by looking at empirical AI benchmark performance over time. This top chart tracks capability accelerating upward, but we must track the derivatives. If velocity is the first derivative and acceleration is the second, the technological jolt is the third derivative, the rate of change of acceleration itself. A sustained positive third derivative signifies that the system's capacity to generate novel solutions is improving at an accelerating pace. This specific curve is driven directly by the automation of cognitive research. Every breakthrough compresses the idea-to-action cycle, rapidly shrinking the time required to achieve the next milestone. This macroscopic curve validates the microeconomic theory. The jolt is the visible footprint of firms successfully substituting silicon for human researchers. Detecting a positive mathematical jolt signifies the onset of a recursive phase transition. Qualitative shifts in global capabilities will occur rapidly, with zero warning. A mathematical capability jolt cannot scale infinitely in a vacuum. It is ultimately bound by the constraints of the physical world. The resource dampening equation shows how a theoretical jolt is modulated in reality. As the system approaches critical physical limits, the effective jolt decelerates. Rmax represents the absolute maximum sustainable level of critical physical resources, terrestrial energy grids, specialized talent, and semiconductor fab capacity. Pushing these hardware limits forward requires highly controlled physical environments and staggeringly complex, slow-moving supply chains. As resource utilization intensifies, the effective jolt magnitude is dampened, dragging hyperbolic mathematical growth back down toward an S-curve saturation point. Overcoming this dampening effect to trigger a true intelligence explosion would require near AGI capabilities to successfully engineer entirely new energy sources or semiconductor architectures. These physical supply chains and energy grids serve as the ultimate friction vectors, preventing immediate, unconstrained intelligence acceleration. The crucial question is how these technological jolts and resource bottlenecks will interact with human society over the next 50 years. Researchers use quantitative scenario models and branching processes to project global economic growth and decline out to the year 2075. These models track the cumulative impact of multiple co-occurring global shocks across 19 distinct quantitative indicators. If we use an additive shock assumption, catastrophic events double the economic damage linearly, but their impacts remain isolated from one another. Under strictly additive assumptions, historical data proves the global economy eventually recovers from extreme systemic shocks within roughly 25 years. But that changes under a multiplicative shock assumption. Highly coupled adaptive systems, like AI infrastructure, climate models, and global financial markets, do not break in isolation. They compound one another exponentially. The models reveal a stark threshold. Triggering a terminal economic decline requires a modest interaction effect across just 3 to 5 co-occurring catastrophes. Because the networks are densely coupled, a localized failure initiates a self-reinforcing negative cascade, culminating in complete and unrecoverable systemic economic collapse. This interaction represents a nonlinear risk. Geopolitical and economic shocks are no longer independent. They are compounded by the speed of AI and quantum development. Managing the 21st century's stability depends on how we navigate these interconnections, recognizing that the difference between a recoverable dip and an irreversible collapse lies in the mathematical coupling of our global systems.